unknown enthalpy in the Born Habor cycle for the production of SrO, right? So strontium oxide solid. And then it gives you like a list of different reactions and then delta H values, or it just gives you delta H values with a number of like, or it'll say like delta H of formation or delta H activation energy. And you have to know what the equation is. So when I look at this equation, I should know what the delta H is, if that makes sense. Some of the homework problems will just say like delta H ionization energy, and you have to know what reaction goes with that. Okay. And so I wanted to kind of go through and work through these reactions so that you get a better idea of what's going on in the process. Okay. And so, here we've got unknown enthalpy. So I have this reaction down here that's part of the Born Habor cycle, and it has a question mark. So in this cycle, we want to know what this enthalpy value is, right? Enthalpy is delta H. It's the heat of the reaction. So, what is this delta H value? And as I've said before, like, here's our reaction, and delta H values can have labels of kilojoules per mole, or sometimes that word per mole is redundant. So you don't have to actually put per mole because it's for 1 mole of strontium reacting with half a mole of oxygen going to 1 mole of strontium. So unless if you don't have the reaction, then you have to write out, or yeah, then you have to say moles. But if you have the reaction, putting that mole is kind of redundant. So sometimes you'll see delta H values that are just kilojoules, and sometimes you'll see them with kilojoules per mole. Okay, and we talked a little bit about the Born Habor cycle on Tuesday. I did one example. And remember, this cycle is a series of hypothetical steps. Okay, and so it's basically saying we can calculate and find different pieces of this based on knowledge that we have. And so with strontium oxide, I can look up all of these different reactions in a table, but maybe I don't know this one, right? And since I don't know this reaction down here, then I can use the other ones to solve it. It's a lot like Hess's law that we did in chapter 6. I think it was chapter 6 that we did it. So what I want to do is kind of look through each one of these questions and assign what kind of delta H this is, okay, or each one of these reactions. And so here I've got strontium solid reacting with half of a mole of O2 gas going to strontium oxide solid, okay? And what I remember from chapter 6 is when I have a product that's made from its elements, so its lowest ground state elements, then this is being formed from those elements. So this delta H is, I'm going to put a little dot, that means standard conditions, is delta H of formation. Okay, and so what the delta H of formation means is whatever our products are, they're being formed from their elements. And I'll say lowest energy form. Okay, so the lowest energy form of strontium is Sr solid, and the lowest energy form of oxygen is O2 gas. And so we make strontium oxide with the elements, okay? And you can write this anytime you have a product, you can write those lowest elements, you just break them into all the different pieces, okay? And so, yeah, so that's the delta H of formation. Next, we have strontium that's a solid, and in this reaction, it turns to a gas, right? And so that's like one of the processes. You have the solid, it goes to a gas, it's subliming. Okay, so this is a delta H sub, SUB. And all that these little subscripts tell us is kind of what the reaction is. So if I just say delta H of sublimation, then you automatically picture this reaction happening where you've got strontium solid going to a gas. So any solid to gas is the sublimation process, okay? Next, we have strontium gas going to strontium plus an electron. So in this process, you've got strontium losing an electron, right? So if it loses an electron, it's undergoing oxidation, remember oxidation reduction. And so since it loses an electron, the energy that it takes to lose that electron is ionization energy. So strontium has lost one electron, so it's the first ionization energy. So ionization of an electron leaves the strontium. Okay, strontium is generally +2, right? So we have to do that process again. You start with strontium plus, going to strontium +2 and losing an electron. So this is the ionization energy, the energy it takes to lose that electron. And I put a little 2 there to say, well, we've already taken one out. Now we're going to take a second one out. So this is called the second ionization energy. Okay. Next, we've got oxygen gas, and look, we're adding an electron to that system. So oxygen in this case is undergoing reduction, adding an electron. So we go from a neutral oxygen to a -1. When we add electron, we talk about the energy that takes place. So this is electron affinity, and we're only adding one electron. So it's the first electron affinity, which is a negative 142 kilojoules. Okay, the next step here, we've got oxygen, which one oxygen is bound to another. That's what it looks like when there's two of them, right? And now the bond gets broken and we have two separate oxygen atoms, okay? So this is a bond together that gets broken. It's called the bond dissociation energy, you'll sometimes see. Okay, sometimes you won't see what is it called? Oh, a subscript. But sometimes you'll see it as BDE. So bonds dissociate, right? They're breaking apart. And then this last one, here I've got strontium 2+ as a gas and oxygen 2- as a gas that goes to a solid, right? And so that process right there, you've got two gaseous ions that come together to form a neutral solid, is lattice energy. So you'll see this as LATT sometimes, or you'll see it as LE, okay? And so there's the lattice energy. And then this last step right here, we're adding another electron. So we've got O-, we're adding an electron to go to O2-. So this is another electron affinity, and it's the second one, right? Because we already have a negative charge, so we're adding that electron, so we're forming a -2. So the second electron affinity. Okay, so that helps me kind of like break down all of the different steps that are in the Born Habor cycle. Okay, so if you, and I'm going to go to the next slide. So if I'm given an equation, you can figure out what delta H it's specifically talking about, right? Because a lot of these delta H values are in a table. Okay, and so if they're in a table, if you're given this reaction, you can actually go and look up these values in the table. But you have to know what the reaction's called in order to do that. Okay, the other thing you have to kind of know how to do is if you're given just the delta H naught of sublimation, you have to know what that reaction looks like, right? So you have to be able to go forward and tell what kind of delta H you're dealing with, and you have to be able to go backwards and decide what the what the reaction looks like if you're just given, you know, this delta H sublimation. Okay, and again, this knot is standard conditions. And for this, it's 25 degrees Celsius, so kind of room temperature, and 1 ATM. So you're doing the reaction out in the open. Okay, and this is important because, you know, it's shorthand for chemists. So I don't want to write like ionization energy every single time. I want to be able to either just write the reaction or just write the delta H value, and you understand what I'm telling you. Okay, so it's chemistry shorthand, because we get kind of lazy too. So are there any questions on labeling these reactions? I'm going to look at the chat window, see if anyone wrote anything in there. I'm going to fix this right here because that should just say 2. Okay, so, you know, I've just gone through and like written up the little subscripts to tell me what those delta H values mean with regard to the reaction. No questions? I'm not clear? All right, Ryan says I'm super clear. Okay, so I had a question written privately to me that said, how do I know how to write the reaction just given the delta H? So if I've got, let's go back to full screen. So if I'm given, so you'll be given 2 pieces of information, right? You'll be given the delta H value, right? And you'll be given what you're talking about. Okay, so if I have an ionization energy, that means ionization energy is losing an electron. And when I have strontium oxide, I know that oxygen likes to gain electrons and strontium likes to lose electrons. And so strontium is going to be the one that loses the electron. Okay, and so with this, you would have to be given that it was a gas, probably to get this exact reaction. But yeah, that's kind of how you go through and figure out what reaction it's talking about. Any other questions about that? Okay, also on this slide, I want to point out too, what I've done is right here, I didn't write this on the last slide because I want to confuse you guys, but generally when you're doing a Born Habor cycle, right, you do it stepwise. So we're doing things like one at a time, one atom at a time, or one electron. You know, so here the atoms are going from solid to gas here. We're going from one gas, we're losing one electron, we lose one electron, we gain one electron, we gain one, right? So everything's done kind of like, I mean, these are like moles of atom, like 1 mole basically. So it's a lot of atoms doing it at once, but we just like to think of things as one at a time. And so you'll notice up here, when we're doing this initial reaction, the heat of formation, we use 1/2 mole of oxygen, right? And so like later on, when we're using this reaction, you know, we only have 1/2 mole. And so what I want to do kind of right now is take this, and it'll make sense when we manipulate these reactions a little bit later, but if I take and divide all of these by 2, okay, so then I have 1/2 mole of oxygen gas goes to 1 mole of oxygen. what I have to do is take my delta H value and divide it by 2 also. So you remember from Hess's law, whatever you do to the elements, or to the reactants and products, you got to do it to everything. So reactants you're dividing by 2, products you're dividing by 2, and delta H value you're going to divide by 2. Okay, and that's just because in the Born Habor cycle, we're doing everything stepwise, like one element at a time. And here we just want to talk about one oxygen atom. Okay, and so like I said, we'll go through that when we actually lay this out. So to me, looking at all these reactions in a list is a little bit confusing, right? Like what is this process? Because, it's kind of a hypothetical process. I know that when I'm gathering chemicals to do a reaction, I know I can get strontium solid, and I know I can get oxygen gas, right? And so then I can form this. So this right here is a real reaction that can take place. And real chemicals I can grab, where some of these others might not be, okay? So when I set this up, I have my heat of formation here. So I start with my strontium solid plus oxygen gas goes to strontium oxide solid, right? So that's my delta H of formation. And so that's kind of like this distance right there. Okay, so here's my reactants, here's my products. So when we're forming something, we've got the reactants, the products. Okay, then when I'm doing this Born Habor cycle, like I said, it's kind of hypothetical, but what I do is I take the elements that I can actually grab from the earth and kind of figure out how to make the product strontium oxide by going through a series of steps. And the top step that we want to get at is the ions in gas, and so we've got strontium 2 oxide, or strontium 2 gas plus oxygen 2 gas at this like peak level. Okay, so when I'm looking at these steps, okay, from strontium solid, to get up to this point, I have to take strontium and make it into a +2. Right? So it has to lose 2 electrons. And when it's losing those electrons, remember that's ionization energy. So from here, I've got to lose 2 electrons. Okay. I also have to go from a solid to a gas. Right? So that's the sublimation that has to happen. And then the last thing is, I've got to go from O2 to oxygen. So I have to break that oxygen-oxygen bond just to have one oxygen atom. Okay, and it's already a gas. So it's already a gas here. So I have to do these, lose 2 electrons, so that's 2 steps. I have to go from a solid to a gas, that's 3 steps, and I have to break the oxygen-oxygen bond. So going from this to this is 4 different steps. Okay. Next, what I need to do to go from, well, actually, let me go to the next slide and I'll explain kind of the last one. Okay, so when I do this, I'm going to go kind of stepwise, right? So I go from strontium solid to strontium gas. Okay, so I'm going to use the delta H of sublimation in this case. Next, I have to lose one of the electrons. So strontium loses 1 electron to become strontium plus, and then it has to lose the second electron. Okay, because these are the processes that have to happen for me to get to strontium 2. And it doesn't matter mathematically which one of these steps I do first. I just know that I need to do these 3 steps to get to the strontium plus part. Okay. And then the last step is we're going to take the oxygen and break that bond. So we have 1/2 oxygen gas goes to 1 oxygen gas. Okay, so we've got delta H of sublimation, we've got delta H ionization energy 1, we've got delta H ionization energy 2, and then we've got that delta H of the bond dissociation energy, or that bond breaking, right? So now I have to figure out a way to get from these products up here, or these reactants up here, down to the main product that I want, right, which is the strontium oxide solid. And I know that if I have the elements, the ions in their gaseous state to go down to the solid, I can use delta H lattice energy, right? That's the definition of the lattice energy. But I have to be able to get that into the +2. So up here, I just have oxygen gas. And so I have to gain 2 electrons to go to O minus. The second one, O minus plus an electron, goes to O2 minus. Okay, and so I've written it this way because I know these have a positive enthalpy value. Well, here's my delta H. Right, so these ones have positive delta H, these ones have negative delta H, and so I kind of write it in these steps to show the direction of whether things are gaining energy, energy is going into the system positive, or energy is leaving the system. And so when I gain an electron in this case, it's losing energy. Okay, so this is the delta H activation energy. And it has to go through those 2 steps. Okay, and then because this is a cycle, right, I have to figure out, and we talked about it earlier, that when we go from the elements to the product, then that's the delta H of formation. Okay, so a lot of times, you know, sometimes I can measure this delta H of formation, but other times I have to, like I said, hypothetically look up these reactions to figure out the energy. You know, it's important because if I was going to do this reaction in the lab, I didn't know what the delta H is. This is the hypothetical process that happens, or I can kind of think through stepwise, like what's happening in this reaction to get that delta H of formation. So when I'm doing the reaction in the lab, like, am I going to release a lot of heat? Am I going to release a little bit of heat? What's actually going to happen? Okay, are there any questions on how I laid this cycle out? I'll minimize and look at my chat window. Or I'll try to look at my chat window. So if you guys have any questions, you can chat them, type them.
So the actual steps that you make, the SR2 plus G and the SR2 plus G plus OG, those actual steps that you make, those are predetermined order, right? Like you have to make sure that you have, anytime you're losing electrons has to be on that step. And once you're breaking elements from O2s to O's or N2s to N's or something like that, it's that second step there, and so on and so forth for the third, fourth step, right?
So this is generally how the cycle's laid out. And that's only because, you know, you've got, like, you know, chemists look at all the reactions. So let me go back to the reaction slide. Can you guys see this? So, you know, chemists look at all these reactions and put all the positive ones on like the left side and all the negative ones on the right side for them to kind of keep track of it a little bit. But you could go through and kind of draw this out in a pathway using these reactions that aren't necessarily in that step. You just would not have like, it goes, you know, you'd have it like sometimes it goes up, over, maybe down a little bit, up, you know, and then up, and then down if you did them in different orders. But you would still end up with the same results, no matter what order you wrote them in, if you went through a logical process.
So it's not like electron affinity has to be in the second step and lattice energy has to be the third step. It can be, okay, got it.
Right, so yeah, you can do them in any order. You just have to be able to draw them you know, like, oh, this is a product of some of the steps, right? So if you could draw out each one of these in a reaction form. So if I started with this, then I lost, or I turned the solid into a gas. So I could actually draw another line right here where I have strontium gas plus 1/2 oxygen. And then I would do the next step where I lost an electron. And then I do the next step where I lost an electron. But then if I use the electron of so if I use the electron affinity, so let's say I started here, and the first thing I wanted to do was break the oxygen bond. Like I would do that first, and it would take energy, so I would go up. And then I'm like trying to point and use my thing. So, and then like, let's say the next step I wanted to do was add that electron to the oxygen. Well, from this, it would go down to. And so I use these arrows based on the delta H values being positive or negative, and that's why I lay out my cycle like this. But if you were to start with the gas here, you know, you'd break the oxygen bond, and then you would like gain your electron and you would go down. But sorry, I'm trying to explain it. So the order you do these steps doesn't necessarily matter, right? The delta H matters, the lattice energy matters, but these steps don't, but you'll end up at the same point, whether you do these ones first or those ones first.
That makes sense. Thank you.
Does it? I feel like it might have been a little bit more confusing.
No, that makes total sense. You can do them really in any order because at the very end, you're going to get to really the same goal no matter what. So yeah, they also equal the same parts. You can add 2 plus 2 either way around. So that makes sense.
Yeah. Yeah, your graph, like this graph of going up and down would just be different, and like what you would put on these lines would be different. This is just kind of conventionally how you have delta H of formation between your reactants and your products, and then your delta H lattice energy on the right side, because it always gives off heat, so you should have a negative number. Are there any other questions about this? Okay. So I'm going to go to the next slide. And here I just have it written up again, so we'll skip. And so I've gone through and I've taken and actually written in the numbers of the steps, right? So here we've got the strontium solid plus the oxygen half gas. And then I've gone through, and from that first slide, I've taken the different reactions that we talked about and wrote their delta H values in. Okay, so strontium solid, again, we go strontium solid to strontium gas. We have the delta H of sublimation. We have the strontium gas losing an electron, so we have the delta H ionization energy. And then we have it losing the second electron for the next ionization energy. So this step right here is made up of 3 parts. Like I was telling Ian, you can break it into 3 different parts. You know, so every time you break, you would have a line horizontal, or like I did it in 3 parts. So, you know, the sublimation is 164 kilojoules. So it just takes a little bit, where the first ionization energy is bigger, and then the second ionization energy is even bigger. So it takes even more energy. Okay, then we have this step where we've got the strontium 2+, and then this reactant just carries over, right? That's in our system. So I have to take the O2 gas and I have to break it to 1 mole. So in this step, like I said, this was the reaction that was given. So what I have to do is take half of that. So if I divide that by 2, I get half. Divide this by 2, I get 1. So I have to take my delta H value and divide it by 2 because I'm only breaking 1 bond. And so this is, you know, this step right here takes 498 kilojoules of energy divided by 2. And then here we've got our oxygen gas and strontium 2+ gas. So down here, we've got strontium 2+ gas plus that goes to O2. So I'm gaining 1 electron. And then this was the delta H that I didn't know when I gained the 2nd electron. Okay, so this is the value that I want to find, is that delta H value right there. Whoops, delta H. Of the electron affinity, the 2nd one. Okay, and then we have the lattice energy where we take strontium 2 gas plus O2 gas, and we can measure that heat release of that, the delta H value. Whoops, I saw there was one of you guys that raised your hand. So is there anything in the chat?
Yeah, I just wanted to ask if I just wanted to clarify if all we need to study for exam 3 is to do like the learning curves of chapter 7 through 9 and the questions on La Lima associated with those chapters.
I would do those. I would also do some practice problems out of the book, like the ones in the chapter, the after the end of the chapter.
You mean the end of the chapters of 7 through 9? Like you practice problems involving those?
Yeah, I mean, it's just a good way to practice. If you're sitting there like, oh, I have some time, how should I study? I wouldn't like read the book. I would do the problems out of the book. I would do learning curves, you know, just give yourself some practice problems that way.
So there's also like practice problems on La Lima as well, right?
Yeah, and there's there's not practice problems on La Lima for those chapters. Okay, so I want to get through this example. So Kylie said, are the delta H sub and ionization energies always given? If not, how do we find them? So the sublimation values up here, ionization energy. So there's actually a table that in your book that has ionization energies, and it will give you like ionization energy and the value, but it won't tell you the equation. So if you know that's the equation that you need, you would go to a table and find it. Okay. At this level, most of the time you'll be given the delta H values that you'll need, but you'll either need to know. So I'll either give you like delta H is this, and you have to figure out what the reaction is to it, or you'll have to solve for the delta H value and know what the reaction is. You can also look at, like in the books, probably the best reference for you guys to find delta H values. You can look them up. They have like huge papers and huge tables for delta H. And so, yeah, that's those are some ways that you can find it. Okay, are there any other questions while we're on this slide? I like when you guys are asking questions. So when I look at this, right, this whole cycle has to kind of equal itself, right? And so here I've just written out, because we're used to looking for delta H values. And your book has a formula that's like, well, this is the basic formula, but I want you guys to kind of understand how this cycle works. And so, you know, I have this delta H value here. And so all the, you know, the delta H value is based off of all of these hypothetical steps that can be done. And so I just wrote up here kind of the delta H value is going to equal all of the make steps, which are on this left side, all the unmake steps, which are on this side. Okay, so if I take and add all of these numbers together, right, I'll get the delta H value. And that's because it automatically factors in whether heat's being gained or put into the system. So this positive delta H value is heat going in, and these ones are automatically negative, so it's the heat going out. Okay, and so if I take and add all of these steps together, I should get this delta H formation value, or I will get it. Okay, so I've broken that down kind of in the next 2 slides. okay, where I've taken the delta H right here, and I'm putting all of the unmake steps and all of the make steps together. So I go through, my delta H value is this negative 592 kilojoules, right? So I'm going to put that in. Next I go, okay, well, I have delta H substitution, delta H ionization energy 1. So delta H substitution, or sublimation, I'm sorry, delta H ionization energy 1, ionization energy 2. I have this delta H value right here, which I wrote right there, and that value has to be divided by 2, okay? Then over here, I have the ionization energy 1, which is right there, and then the 2, ionization energy 2 is the one I'm looking for, so I put that in bold. So we know, okay, this is the one we're solving for. And then the last one is the lattice energy, which is there. Okay, so I've gone through every one of my hypothetical steps and added them together to get this delta HF. Okay. So the next slide, I went back to the beginning, right? I've got my delta H of formation reaction. I've written all of the steps that were in my whole entire cycle in this reaction. And I want to know what the delta H of this activation energy 2 is. Okay. And this is the reaction from that very first slide that I wanted to find out. So I have a negative oxygen gas plus an electron goes to O2 minus gas. Okay, so this delta H right here is what I'm looking for. So in this whole step, I need to solve for delta H electron affinity. Sorry, that word always like leaves me. That electron affinity 2. Okay, and so to do that, I've got my delta H of formation on this side, and then I'm going to subtract all of these values over, right? So delta HF minus delta H of sublimation minus ionization energy 1 minus ionization energy 2 minus electron affinity 1 minus that bond dissociation energy minus the lattice energy, okay? And that gives us the delta H of the activation energy, okay? So then I went through, or not, electron affinity. I'm going to write that down. Okay, so my electron affinity 2. So I've gone through my delta H of formation is negative 9 or 592. Then I've got minus the sublimation, minus the ionization energy, minus ionization energy 2, minus ionization energy 1. And then, so this ionization energy, remember, was negative, so that's why there's the positive number there, minus the bond dissociation energy. Okay, which is that number divided by 2, like I said. And then lattice energy is negative, and so negative times negative is a positive. So that's where I get those numbers. So the delta H of electron affinity 2, so the second electron I'm taking away from oxygen. Let's see, I did all this, is 741 kilojoules. And so, yeah, when we go through those steps, then we'll get the ionization energy of making that electron, or adding that electron to the system. So I guess the biggest takeaway from these is, we're going to do a Kahoot in a second, is being able to go through and assign different reactions to the steps. Okay, so you should be able to know what reactions go in the steps. And then the second thing is well, I guess the other two things is if I give you in a reaction, you should be able to tell me what kind of delta H it is. So is it a sublimation? Is it an ionization energy? Okay. Is it an electron affinity? And then the last thing is if I give you ionization energy 2 and I give you strontium 2+, you should be able to come up with this reaction. So those are kind of the three main things that I want you to know in this Born Habor cycle is being able to recognize the reaction and the delta H value together. And then also, you know, if I give you a layout like this, you should be able to put put reactions into the different spots.